time for math in the house. This is Calculus, Chapter 7, Section 7. All right, let's get started. So, we've got the integral from 0 to 1 of e to the x squared dx. Go ahead and get started on that. That's my joke again. You have no idea what you're doing here. Okay. This is an integral that cannot be done by any method that we know. And basically, if we want to get the value of this integral, we need an approximation. And we can get an approximation as close as we want, but we definitely do need to approximate it because there's no way we can do it by any calculus method. So that's why we're talking about approximate integration. Okay, so there are going to be 3 basic approximations for integration. So check out your book on page 518, and you see the right hand, well, okay, first the left hand approximation. So we've got, well, yeah, just go ahead and check it out in the book. Page 518, you see that the left hand approximation is where each corner of the rectangle on the left side hits the curve. Now the right-handed approximation is going to be each right corner of the rectangle is going to hit the curve. So for the left-handed, the height of each rectangle is going to be the height of the left side of the rectangle. And the right-handed approximation, the height of each rectangle is going to be the height of the right side. Now the midpoint approximation is going to, the height of each rectangle is going to be the height at the midpoint of each rectangle. Okay, so the midpoint approximation is going to be capital M sub n, which means we're going to do a midpoint approximation with n rectangles. So our integral from a to b of f of x dx is going to be approximately equal to the midpoint approximation. Now what's that going to equal? Well, we've got delta x times f of x. So rectangles are going to be width times height. Delta x is b minus a over n, which means b minus a is the entire width that it's going to encompass, divided by the number of rectangles that we want. And this will be a finite number of rectangles. So we've got the delta x, the width of each rectangle, times the height of each rectangle. Now what's the height of each rectangle? Well, it's going to be the height at the midpoint of the rectangle. The midpoint then is going to be the left edge plus the x value at the left plus the x value at the right divided by 2, which is the average of the two x values, which is the x value at the middle of the rectangle. And so x sub 2 bar, this is the average of x sub 2, which means you're going to take the x sub 1 plus x sub 2 divided by 2, or the left edge plus the right edge divided by 2. That gives you the middle. And likewise, x bar sub 3, or x sub 3 bar, is going to be the average of the x sub 2 and x sub 3. So, now when you add each rectangle up, you're going to get the midpoint approximation of the entire region. Now, this is going to have an error associated with it. It's not going to be exact. It's going to be off by this amount. So this is the error. E sub m is the error of the midpoint, and we have it in absolute value because the error could be high or it could be low. So basically it could be above or below the actual volume under the, or the actual area under the curve could be above or below the estimate by the midpoints. So this error is less than or equal to, or basically what we're saying is the error is within this amount. And this amount is going to be k times b minus a cubed over 24n squared. Now, b is the right endpoint, a is the left endpoint, so you're basically taking the x distance from a to b and you're cubing it, and then you're going to divide by 24 times the number of rectangles squared, and now we're going to multiply by a k value. Well, the k value is a value that we're going to choose, and the only thing is the k value has to be at least as great as the value of the second derivative of the function between a and b. That's it. So this is midpoint rule. This is error of the midpoint. Now we're going to look at a second type of approximation, and that's going to be the trapezoidal rule. All right, the trapezoidal rule, okay, if you take a look at figure 2 on 519, page 519, you're going to see that we're going to divide the area under the curve into trapezoids instead of rectangles. Now, this area is going to be approximately delta x over 2 times f of x of o plus 2f of x of 1 plus 2f of x of 2 plus 2f of x of 3 plus 2f of x of 4, and just keep going 2, 2, 2 until you get to the next last one is still 2 times the height. The last one is 1 times the height. Now, delta x is still b minus a over n. Okay, now I want to explain why this is 2, 2, 2. So let's take a look at okay, if I've got some trapezoids here, okay, so here's x of o, here's x of 1, here's x of 2, here's x of 3. So this height is going to be f of x of o. And this height is going to be f of x of 1. This height is f of x of 2. And this height is f of x of 3. Now, we know that the area of a trapezoid is going to be 1/2 times the average of the bases times the height. Well, let's draw a trapezoid here. So, well, okay, yeah, let's... Okay, here's a trapezoid. Now here's B1 and here's B2. And the height is this distance here. So, notice the area of a trapezoid is basically the area of a rectangle where you don't have the same base. So we know the area of a rectangle is base times height. Well, we'd like to go base times height here, but the bases are different. So that means we have to take the average of the two bases times the height. So that's the area of the trapezoid, is the average of the two bases times the height. Now, in this case, the bases are the vertical distances. So f of x of o, f of x of 1, f of x of 2, f of x of 3 are the bases. Okay, so let's let's look at then the area here is going to be it's 1/2 times, let's just do this, 1/2 times f of x sub o plus f of x sub 1 times the height, which is f vector, or which is delta x. Plus, that's our first trapezoid. Now our second trapezoid is going to be 1/2 times f of x sub 1 plus f of x sub 2 times delta x. Plus, the third trapezoid is going to be 1/2 times f of x sub 2 plus f of x sub 3 times delta x. All right, so let's add these up. We've got, notice, 1/2 f of x, or 1/2 delta x times everything. So I can put this as delta x over 2 times, now I've got f of x sub o plus f of x sub 1 plus another f of x sub 1. So that's 2 f of x sub 1 plus f of x sub 2 plus another f of x sub 2. So that's plus 2 f of x sub 2 plus f of x sub 3. So notice we have 1 times the first height and 2 times every height until the end, where we have 1 times the last height. Why is that? Because when we look at this trapezoid, this f of x sub 1 is sharing the heights on, or these two trapezoids are sharing f of x sub 1. And these two trapezoids are sharing f of x sub 2. So every trapezoid, every f of x in between the first and the last has to be doubled because they're shared. And the first and last are just single. So that's why our midpoint rule, that's why our trapezoid rule is delta x over 2, and then it goes 1 f of x, then 2, then 2, then 2, then 2, then 2, all the way to the very end where it's 1 again. Okay, so you want to memorize that, obviously. Okay, now, the error in the trapezoid method is going to be our k times b minus a cubed over only 12n squared. So, if you look at the figure 1 and figure 2, it really seems like the trapezoid method is a closer approximation. But that's not true. If you notice the formula for error, the trapezoid is divided by 12. Error of the trapezoid is divided by 12, whereas error of the midpoint is divided by 24. So the error of the midpoint rule is going to be exactly half the error of the trapezoid rule. Or the error of the trapezoid is twice the error of the midpoint. Okay, here's an example. Here's a sketch of why that would be. So if our curve between A and B is this green curve here. Now, the trapezoid would just cut the curve off from beginning to end. So the trapezoid, the error in the trapezoid would be the blue section. The error in the midpoint would be the red section. So the blue section is exactly half or I'm sorry, the blue section is exactly twice the error of the red section here. So those are our two linear approximations. Trapezoids and midpoints are both rectangles with, so the area is linear. Now, let's go to a third technique that's a lot more accurate. Okay, third technique is called Simpson's rule. And Simpson's rule is based on parabolas. So if you check out page 522, you see at the bottom of the page, what Simpson does is instead of using rectangles that are squared off, he used parabolas that are rounded, so the parabola more closely approximates the curvature of the curve. So there's a lot less error in Simpson's rule. Okay, now, here's Simpson's rule. It's delta x over 3 times fx of O plus 4fx of 1 plus 2fx of 2 plus 4fx of 3 plus 4, 2, 4, 2, 4, 2, 4, 2, as long as it goes. And the last ones have to be 2, 4, 1. So, it always has to go 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So there has to be a 1 at the beginning and the end. There has to be 4s in the second and the second to the last, and then alternating 4s and 2s from there. So delta x is still b minus a over n. But note, n must be even here. Because if n isn't even, you're not going to be able to get your 4, 2, 4, 2, 4, 2 in. And now, like I said, this is far more accurate than the midpoint approximation or the trapezoidal approximation. So the error for Simpson is going to be k times b minus a to the 5th divided by 180 n to the 4th. Now, k is different here. K isn't just within the second derivative, it's within the fourth derivative. So you take the fourth derivative of the function, and k is going to be at least that much. Now, when we pick a k, like I told you, we actually choose a k. We want k to be convenient. We don't want k to be some decimal with, 18 decimal places. So all you do is round k to the nearest whole number. So if it ends up being 0.00347, you just round it up to 1. So no matter what this turns out to be, you're going to round it to the nearest whole number. Why? Because that's going to make this higher than it really needs to be, but we want to make sure that our error is at least as much. Like, we don't want to underestimate the error. So if you're building a bridge, you want to definitely make sure everything is oversized. You don't want to have it undersized and have somebody crash through it driving across. Okay, so now we just need to work out some example problems. The thing about this lesson is there isn't anything complicated. It's just a matter of remembering these three formulas. So you have to remember the rules themselves. So we've got midpoint, we've got midpoint, trapezoid, and Simpson's rules. And then we have midpoint error, trapezoid error, and Simpson error. So basically 6 different formulas you have to remember, but any given formula isn't difficult. Okay, so let's try some example problems. Okay. All right, so we're going to do the trapezoidal rule and the midpoint rule with 5 rectangles to approximate the integral from 1 to 2 of 1 over x dx. Okay, now we could actually determine this integral, but we're going to use our approximation methods to do it instead. So we're going to have 5 rectangles from 1 to 2, and let's see, what else do we need to know? That's it. Okay, so 5 rectangles, n equals 5, a is 1, b is 2. And so first we're going to do the midpoint. So the midpoint with 5 is going to be the b minus a over n. So 2 minus 1 over 5. So there's our delta x times, now we need the midpoint. The first rectangle is going to go from 1 to 1.2. So we want the midpoint of that, which is 1.1. Then the midpoint from 1.2 to 1.4 is 1.3. Then the next midpoint is 1.5, then the next midpoint is 1.7, and the last midpoint is 1.9, which is the rectangle that goes from 1.8 to 2.0. So now all we do is plug those in, and this gives us 1/5 or 0.2 times f of 1.1. So that just means 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. And we crank that out in our trusty calculator, and we end up with 0.691908. Okay, so there's our midpoint. Now we want to do our trapezoidal approximation. So our trapezoidal approximation is going to be delta x over 2. So we still have our same delta x, which is 0.2. So it's going to be delta x over 0.2 times f of x sub 1, which would be, or I'm sorry, f of x sub o. So f of, now x sub o is going to be 1. Now f of x sub 1, that's going to be 1.2. So we have 2 times f of 1.2 plus 2 times f of 1.4. Ah, rats. Yeah. We didn't need that parentheses. Plus 2 times f of 1.6 plus 2 times f of 1.8. Wait a minute. 1, 2. Oh yeah, that's right. Plus f of 2. Yeah, I was thinking there was going to be 5. There has to be 6. There has to be one more because you have f of x sub o and f of x sub n. So this is our trapezoidal approximation. So we end up with 0.1 times 1 over 1 plus 2 over 1.2 plus 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8 plus 1 over 2. Now we add those puppies up and we end up with 0.695635. Now, the other thing just to think about is the function is 1 over x. So the function is going, we're going from 1 to 2. So here's 1 to 2. And so at 1 we've got 1, and at 2 we've got a half. And so our curve looks like this. Nice. That's not actually a curve, huh? Okay, so now the midpoint approximation is going to be slightly above. No, I'm sorry, slightly below. Midpoint approximation goes like this. So the red is the midpoint, and that's going to be slightly below the curve. Now the blue is going to be the trapezoid, and that's going to be above the curve. So the blue is the trapezoid, so it's above the curve. So you notice the trapezoid estimate is higher than the midpoint estimate, which is what we would expect. So good thing, it appears we did it right. Okay. Now, let's try an example with Simpson. Yeah, you know, we'll just do the same one with Simpson's rule. Okay, so we're going to do integral from 1 to 2 of 1 over x dx, 5 rectangles. So A is 1, B is 2, and we'll do Simpson's rule. So S sub 5 is going to equal, oh, rats, you can't do n equals 5, because n's not an even number, idiot. Okay, so, not supposed to laugh while I'm recording. Okay, so let's make n equal 10. So there's an example in the book that has 10. I was just wondering why that could be, but now we know. So Simpson for 10 is going to be delta x over 3. So that's b minus a over n. So 2 minus 1, b minus a over n divided by 3 times, okay, now we go f of x sub o, which is going to be f of 1, plus 4 f of, now we're going every tenth. Each rectangle is 1/10 wide. So that means the f of x sub 1 is 1.1, plus 2 f of 1.2, plus 4 f of 1.3, plus 2 f of 1.4. I'm not going to do the dot, dot, dot. I'm going to show you every single rectangle. So we're going to go plus 4 f of 1.5 plus 2 f of 1.6 plus 4 f of 1.7 plus 2 f of 1.8 plus 4 f of 1.9. Now we're at the next to the last one, so now we just go f of 2. That's it. Now let's crank this puppy on out. So we've got b minus a over n, so we have 1/10 divided by 3. So let's just do that, 0.1 over 3 times f of 1, so we've got 1 over 1 plus 4 over 1.1 plus 2 over 1.2 plus 4 over 1.3 plus 2 over 1.4 plus 4 over 1.5 plus 2 over 1.6 plus 4 over 1.7 plus 2 over 1.8 plus 4 over 1.9 plus 1 over 2.0. Okay, and when we crank that puppy out, we end up with 0.693150. So S sub 10 equals 0.693150. That's actually right. Okay, so now we've done the approximation for the midpoint rule, the trapezoidal rule, and Simpson's rule. So now all we have to do left is talk about error. Error, Will Robinson. You guys are too young to remember that. I'm recording now. We're in the show.
Yes.
Okay, so next thing, we're going to calculate the error in each of these methods. So all right, let's just calculate the error in all three methods that we just used just now. So, so we did the midpoint approximation from 1 to 2 of 1 over x dx. So we want to get the error of that. So all right, error of midpoint. Now, first of all, we need to find k. So the error of the midpoint is going to be k times b minus a cubed all over 24n squared. Now, we've got, actually it's not equal to, it's less than equal to. Alright, so f of x equals 1 over x. So f prime of x equals, well, 1 over x is x to the negative 1. So f prime of x is going to be x negative x to the negative 2. And then f double prime of x is going to be 2x to the negative 3. So that equals 2 over x cubed. Now, what we want to do is choose a k value that's at least that much. Now, we're looking for x has to be between a and b. So x goes from 1 to 2. Now, if we let x be 2, then my f double prime is 2 over 8, which is 1/4. If we let x equal 1, then it equals 2 over 1, which equals 2. Now, we want the largest k value possible. So what we're going to do is we're going to say let k, let's see. Okay, so we're going to let k equal 2. Because 2 over 1 cubed. All right, so we're letting k equal 2. So that means our error is going to be within 2 times 2 minus 1 quantity cubed over 24. And we took 5 rectangles, so times 5 squared. So that error is going to be within 2 over 24 times 25. So 24 times 25 is 600. 2 over 600 is 1 over 300, which is 0.003 repeating. We don't want to mess that up, so let's actually calculate it. So I've got 2 over 24 times 25. Yeah, that's right. 0.003 repeating. How could I have doubted myself? Okay, so this is 0.0033. So the error of the midpoint is going to be within 0.0033. Okay, now let's check out the error of the trapezoid. So we still have our same k here. So the error of the trapezoid is going to be within still 2 times 2 minus 1 quantity cubed. But this time it's only divided by 12 times 5 squared. So the error of the trapezoid is going to be twice that. So it's 0.0066 repeating. So there's our error of midpoint, error of the trapezoid. Now, let's do the error of the Simpson. Now this is going to be a little bit different because the K is different. The N, we took more rectangles, so that's going to be different. And the B minus A is the same. Okay, so let's do that. So, yeah, we might as well just start here. So this time, we need the fourth derivative. So, f of x is x to the negative 1, f prime is negative x to the negative 2, f double prime is 2x to the negative 3, f triple prime is negative 6x to the negative 4, and the fourth derivative is going to be 24x to the negative 5. Okay, so that means f to the fourth derivative of x is going to equal 24 over x to the fifth. Now, if x is 1, then we've got 24 over 1. If we've got x equal 2, then it's 24 over 32. Now, the largest possible k value is going to be when x is 1, so we're going to let k equal 24. Okay, so now our error for Simpson is going to be 24 times b minus a to the fifth over 180 times n, which remember we took 10 rectangles this time, so it's going to be 10 to the fourth. So that's 24 over 180 with 4 zeros at the end. So 24 over 180, 1, 2, 3, 4. Bam! 1.33 times 10 to the negative fifth. Oh, and so actually, remember, it's not equal to, it's less than or equal to. So that's going to be 1.33 times 10 to the negative fifth, or 0.0000133. So that's it. We've got the error of the midpoint, trapezoid, and Simpson. And remember, Simpson should be a lot smaller because it's a lot more accurate than midpoint and trapezoid. Okay, now, there's only one more type of problem that we're going to do, and that's where, see, we've taken a certain, we've gotten the area by 3 different methods, and we've calculated the error of each of those methods. But the next thing we want to do is say, if I want to do, if I want my error to be a certain level, then how many rectangles do I need with each given method? So if you take a look at take a look at example 2. How how large should we take n? In other words, how many rectangles do we want in order to guarantee the trapezoidal and midpoint approximations for our area, the integral from 1 to 2 of 1 over x dx, are accurate to within 0.0001. Now, that's actually more typical of how things work in industry. The customer is going to tell you what accuracy he wants, and it's up to you as the engineer to give him that accuracy. So you know, the more rectangles you use, the more accuracy you have, and so they're saying we want it guaranteed within 0.0001, and how many ever rectangles it takes, you do it. Okay, so let's check that out. All right. Let's see. Yeah, let's just start right here. This time, what we're going to do is we're going to say the error has to be within 0.0001, and k, we already know, equals 2. Let's see if the book actually did k equals 2. Yeah, okay, k equals 2, that's happening. All right, so let's check that out then. So what we're going to do is we're going to say the error, 0.0001, has to be less than or equal to k times b minus a cubed over 24 times n squared. And n is what I don't know. So we'll just say, we're going to make this an equal sign. So now it's time to solve for n. So basically 2 times 1 is 2, so we've got 0.0001 equals 2 over 24, or 1 over 12n squared. So that means, yeah, we'll just multiply both sides by 12. So, yeah, 12 times 0.0001 equals 1 over n squared. So that means n squared equals 1 over 12 times 0.0001. And so n equals the square root of 1 over 12 times 0.0001. Okay, so n should equal 129.099. Now, 129.099, it's tempting to just say, well, let's let n equal 129. But if we let n equal 129, then we don't have the accuracy that the customer demands. So we have to let n equal 130 to be guaranteed of it. So let's see what the... Something has gone awry. Let's see, what happened here? 2 2 over 24n squared, which is 1 over 12 n squared, let's do that again. Okay, if we just start up here, 2 over 24 is 1 over 12. And then I'm just going to multiply, so I'm going to take my 0.0001, multiply by 12, reciprocate the whole thing, and take the square root. So what the heck was I doing? Okay. I would edit this, but you guys are used to me screwing up. So, okay, all you do here is multiply the 12 over, then reciprocate the whole thing in the calculator, take the square root of the whole thing, and n ends up being 28.867. So, we want to choose 29 rectangles to be guaranteed the accuracy 0.0001. Now, notice this rounds up, but like I said, if it turned out to be 28.001, you still have to make it 29. All right, now, let's do the trapezoid. If we're using the trapezoidal method, then that means 0.0001 equals 2 times 2 minus 1 cubed over 12 n squared. Okay, so now I'm going to make this, it's going to be 1 over 6n squared. So, I punch in my 0.0001, then multiply by 6, then reciprocate the whole thing, so that's n squared equals what's in my calculator, and then I take square root of the whole thing, and I get 40.82. Yeah, so that means I'm going to need 41 rectangles for the Okay, so in order to get the same accuracy, if I'm using the midpoint approximation, I can use less rectangles. If I'm using the trapezoidal approximation, then I need to use more rectangles. Now, it's not exactly twice as many because we've got the n squared in the function. Okay, so let's do one more thing. Let's calculate the number of rectangles that we need in the trapezoidal method for 0.0001 accuracy. Okay, so for the trapezoid, we said k is 24. I'm sorry, yeah, for Simpson, k is 24. So with k equal to 24, then what we're doing is we're saying 0.0001 accuracy is going to equal k times b minus a to the fifth over 180 n to the fourth. Okay, so I'm going to do this whole thing in my calculator because I've already been proven to be inaccurate when I do it on the board. So I punch in my 0.0001. Now I go times 180 then I divide by 24. So what I have left is 1 over n to the 4th. So I reciprocate that. Now I have n to the 4th. So now I take the 4th root of what's in my calculator, or I just take it to the 0.25 power. And I end up with n equals 6.04. So, how many rectangles do I choose? Right, 7. Choose 7 rectangles. So notice how much more accurate the Simpson's method is, because we only need 7 rectangles for the same accuracy as it took us 28 or 29 and 41 rectangles in the other 2 methods. So that's basically it. Like I said, there's nothing difficult in this lesson except remembering your formulas. So have fun with these.
Satisfied.